Assalamualaikum warahmatullahi wabarakatuh, and welcome to the fifth video lesson for your physics online learning. For this for this lesson, we will continue from where we left off last time. So last time we learned about decay equations. So you should be right now already know how to construct the decay equations, and also you should by now already know what happens to the nucleus when you have an alpha decay, beta decay, and also gamma decay. For this topic, we're going to look at half-life, and these are the learning objectives. So the first learning objective is you get to learn what we mean by half-life. So what is the definition of half-life? And then the second objective, which is, and also the second thing that we'll look for this lesson, we'll look in this lesson, is how we do calculations using half-life. Okay, let's start. Here I have an animation, and in this animation I want to show you what happens when an atom decays or a radioactive atom decays. So this animation shows the decay of the alpha decay of polonium. So as you can see, this is a single polonium and then it decays into lead. So let's see that again. So polonium, and then the polonium is the parent nucleus. It's the original nucleus before it's decayed, and then it becomes the daughter nucleus, which is lead. Okay, it turned into a new element. Now let's look at what happens if you have a lot of polonium. Okay, so let's say in this case you have 41 polonium, and let's play the animation. And one by one, the polonium becomes lead. Okay, so this is actually what's happening inside the substance, inside the radioactive substance. So each of the atom or each of the nucleus will slowly one by one decay. And remember, decay is radioactive decay is a spontaneous process, so you cannot really predict when it's going to decay. And this is the sort of thing that you should see. Right, radioactive decay and half-life. When you consider the decay of an unstable nucleus, it's not as straightforward as it seems. So let's say you have a radioactive substance, and the radioactive substance all have atoms right in it, and the atoms don't all everything decay all at the same time. They will decay one by one, and you cannot predict when each atom will decay. So it's not as straightforward as it seems. Say if you have 100 grams of uranium and it is decaying. And let's say after 2 days, the mass of this uranium becomes half, right? So 50 grams. And then, so by logic, you would expect the remaining half to decay in the next 2 days. But actually, that doesn't happen when it comes to radiation. What actually happens is something like this, something that is shown in this table. So let's say at the beginning, it has 100 grams of mass, and time is 0, so that's at the beginning. And let's say after 10 seconds, right? So 10 seconds, the mass becomes 50 grams. So you would expect when it becomes 20 seconds, when the time is 20 seconds, you would expect the mass to become 0. So the other half should decay by now. But actually, it becomes 25, which is half of 50. If you wait for another 10 seconds, it becomes half of that again. Okay, so as you can see, for a specific time, the mass halves every time. Now let's see what that looks like on a graph. So this is what the graph looks like. This is a graph of mass against time. On the y-axis, we have mass in grams, and on the x-axis, we have times in second. If we draw a graph of the table just now, it will look like this, right? So when time is 0, the mass is 100. When time is 10 seconds, the mass is 50. When time is 20, the mass is half of 50, which is 25. When the time is 30 seconds, the mass is half of 25, which is 12.5. So as you can see, every 10 seconds for this substance, it becomes half. So from 100, it becomes half to 50, and it halves again to 25, and becomes half again to 12.5. This is how a radioactive substance decays. A radioactive substance doesn't decay as straightforward as you would think. It decays in this sort of trend. This type of curve is called the decay curve because it's a curve that shows how the radioactive substance decays. Apart from mass, we can also put other units of radiation or radioactivity on the y-axis. So you can put mass on the y-axis, you can put number of atoms or count rate or activity. So these are just units of radiation, and there are a lot of units for radiation. So you can use that, and the graph, the shape of the graph will also be the same. So it should look like a curve. If you look carefully at the graph and table, you would notice that for every 10 seconds, the mass is divided by half. The time, which is 10 seconds, in this case, is known as half-life, right? So for this graph, for this radioactive substance, we say it has a half-life of 10 seconds. So what is half-life? Half-life is defined as the time taken for the radioactive nuclei to decay by half. So it is a quantity that is related to time, not life, but time. So how much time does it take for the radioactive nuclei to become half? So that is the half-life. The half-life has a symbol T and then a subscript or a small half at the bottom right corner of the T. So that is the symbol for half-life. And because half-life is a quantity of time, it is measured in seconds or minutes or hours, days, weeks, months, or even years. This is a table showing the half-life of different isotopes, radioactive isotopes. So for uranium, you can see it has a half-life of 4.5 times 10 to the power 9 years. So that is a very long time for it to become half. In other words, it takes a very long time for uranium to decay, right? For carbon, it is 5.7 times 10 to the power of 3 years. So again, a very long time. Not as long as uranium, but still quite long because that is actually 5,700 years. That's quite a long time. Radium is 1.6 times 10 to the power minus 3. So that's 1,600 years for it to decay. And to decay by half, not decay completely, to decay by half. Strontium, 28 years. Iodine, 8.1 days. Bismuth, 19.7 minutes. Polonium is quite quick. It is actually 1.5 times 10 to the power minus 4 seconds. So that is probably 15 milliseconds. So that's very quick. So as you can see, different isotopes, different radioactive isotopes have different half-lives. And this is an example of what happens inside the radioactive isotope in terms of its atoms when it is decaying. So at the start there are 16 radioactive atoms, and then after one half-life, half of them have decayed, so that becomes 8. And then after two half-lives, another half have decayed, so you are left with 4 atoms. And then after 3 half-lives, another 2 have decayed, so you now have less than what you have in the beginning. Here's another example of half-life, of how you can look at half-life. So in the beginning you have 100 grams, and then it becomes half of that decays and it becomes a new element. That's why you have a blue bar there. And what's left of the old, the non-decayed nuclei is 50 gram, and then half of that decays again, it becomes 25 gram, and then another half decays, then it becomes 12.5 grams. Okay, so for every half-life cycle, so first half-life, second half-life, third half-life, the radioactive isotope decay. Let's do an example to see how we use half-life. Okay. So example 1, A. From the graph, what is the half-life of the isotope? So as you can see here, the graph on the y-axis is counts per minute, and on the x-axis it is in years, in time, years. So when the time is 0, so at the beginning, it has 3,000 counts per minute, and then when the time is 1 year, it has 1,500 counts per minute, and then when the time is 2 years, and it's 2 years, it becomes half again, which is 750 counts per minute. So what is the half-life of this radioactive isotope? So you just have to figure out the time it takes for it to become half. So in the beginning, it has 3,000 counts per second, counts per minute, and then after how long does it take to become half? So half of 3,000 is 1,500, and the time it takes to become half is actually this period here, from 3,000 to 1,500, and that is actually 1 year. So 1 year is the time it takes for the radioactive isotope to become half, and therefore the half-life of the radioactive isotope is 1 year. Let's confirm this if it's correct. So you should see for 1,500 to become half of that, that is for 1,500 to become 750, which is half of that number, it takes another 1 year. So every 1 year it becomes half. So that is correct. 1 year is the half-life of this radioactive isotope. B, continue and complete the graph. So after 3 years, what should the graph look like? So we know that the half-life is 1 year. So from the second year to the third year, the counts per minute should half again. So from 750 to become half of that, so it should be around here. It should become 750 should become 375. Okay, so it should be around here. And then the graph will look like this. So let's just continue the curve, and the curve will look like that, right? C, when will the isotope decay from a maximum of 3,000 counts per minute to a count rate of 375 counts per minute? So how long does it take for it to go from 3,000 counts per minute to 375? So we have the answer right here in front of us on the graph. It actually takes 3 years. So the amount of time it takes to decay from 3,000 to 375 is 3 years. Okay, and those are the answers for this example. Example 2. A radioactive source gives a reading of 640 counts per second when measured using a GM tube. 1 day later, the reading drops to 40 counts per second. What is the half-life of this source? So in this example, you start with 640 counts per second. So that's what you started with. And this will decay, of course, and become less. And then 1 day later, it becomes 40 counts per second. So that's at the end. And we want to know what is the half-life of this source using this piece of information. Okay, so let's do this example. We'll do the example 2 here. So the question says that at the start you have 640 counts per minute, and then at the end you have 40 counts per minute, and that takes 1 day. And then the question is asking what is the half-life. When it comes to calculations with half-life, there is no formula for this at this stage. But what you have to do is you have to use logic, and you have to use common sense, and you have to have some sort of timeline. Okay, so let's change the day to hours because that's easy. That's easier for us to do. So instead of days, let's change it to hours. So one day is 24 hours. You can even change this to minute, but we don't need to do that. So you need to have some sort of timeline in this case. So let's draw a table. And when it comes to questions, I'm sorry if my table is ugly. And when it comes to question on radioactivity, I mean half-life, having a timeline or having a table is what helps you with your calculation. So on this side of the table, we have the counts per minute. And on this side, we have the time. Okay. So in the beginning, we have 640 counts. So that is the beginning. So that is 0. Time is 0. And then when we don't know when is the time for the next decay, but after a certain time, after one half-life, what should happen is that, so let's say this is the first half-life cycle, and this will be the second half-life cycle, and let's just write down 2 for the time being. So after one half-life, the 640 becomes half. So 640 divided by 2 is 320. Okay, and then after another half-life, the 320 becomes half again. So 320 divided by 2, that is, I think, let me grab my calculator here, 170, 160. Okay, and we have to go again. So half of 160, so another half-life, so the third half-life this time. Half of 160, that is 80. And then we have to go again. So the fourth half-life cycle. So 80, it becomes half again, then it becomes 40. Okay, and that is our goal. So we want to start from 640 according to the question, and then we should end up with 40. Okay, so to get from 640 to 40, it takes about 4 half-life cycle. In other words, it halves 4 times. So 1, 2, 3, 4. Okay, it halves 4 times. And all of this takes in 24 hours. So here, the time should be 24 hours. So what we need to do is we just have to figure out the interval between these half-life cycles. What is the interval? Okay, so how do we find the interval? So in 24 hours, it has half 4 times. So that means 24 divided by 4. And then that will give you 24 divided by 4. That is 6 hours. Right? So in other words, this is the answer. Right? So every 6 hours, it becomes half. In other words, if we look at the table here, so 0 times 6 hours, it becomes 320. And then another 6 hours, so that's 12, it becomes 160. So another 6 hours, that becomes 118, and that becomes 80. Another 6 hours, that becomes 24 hours, and that becomes 40. So the answer, the half-life, is 6 hours, and that is the answer. Okay, for example 2. Example 3. A radioactive material has a half-life of 48 seconds. Its activity is 16 counts per second. What was its activity 6 minutes 24 seconds ago? So let's underline the key information here. So half-life of 48 seconds, and its activity is 18 counts per second. So that is the activity now. What was its activity 6 minutes 24 seconds ago? Okay, let's do this example. Right, so for this one, let's write down the information right here. So it has a half-life of 48 seconds, and then its activity. So activity is a unit for for the radiations. It shows you how active the radiation is. So the activity is activity that is now, that is 16 counts per second, and then it wants to find what is the activity before, okay, which is 6 minutes, 6 minutes, sorry, 24 seconds ago, okay. So because the half-life is in 48 seconds, we just want to convert this into seconds. So 6 minutes, 24 seconds into seconds. We just convert this into seconds to make our lives easier. And that is 384 seconds. Okay, just like before, you need to draw some sort of table here. So let me just draw this table. Hopefully it won't be an ugly table this time. Okay, it's still an ugly table. So on the left side, let's just write down the activity. And on the right side, let's write down the time. So the time is in seconds. Okay, so we have the number of activity now. So this is now 16, which is time 384 seconds after. What we want to do is we want to go backwards. Okay, we want to go backwards in time. So first we have to figure out, for this amount of time, how many times does the radioactive isotope becomes half. So for 384 seconds, how many times does it half? So what you can do is, that's the total amount of time, 384 seconds. And then you have a half-life of 48 seconds for this radioactive isotope. And we did that time period. So how many times it half? Okay. And 384 divided by 48, that is 8. So in other words, 8 times. So in order to, we have to work backwards from here, work backwards 8 times to figure out the activity before. Okay, so we have to go back for 8 steps. So let's just, okay, so 16, go backwards. So you have to calculate a number. When you have that number, it becomes 16. So in other words, you have to double 16. You double 16, that is 32. That is the first step backwards, and then we do another step backwards. So that's the second. Okay. Let me just complete this table. So first, second, third, fourth, fifth, sixth. Do I have enough space here? Okay, we'll see. So first, second, third, fourth, fifth, sixth, seventh. Okay, I don't have enough space. Let me just squeeze in one right there. I'm sorry if it's not that pretty, but at least you get the idea. Okay. Let's not worry about the time in this case. So 16 to 32. So that's the first half-life cycle. And then 32 going backwards in time. That becomes 64. And then 64, double of that is 128. And then double of 128 is 256. Double of 256 is 512. Double of that is 1024. double that again is 2048. Double that again is 4096. Okay, and we have arrived at the activity when the time is 384 seconds ago. So the answer to this question is 4096 counts per second. That's the answer. Okay, in other words, 6 minutes 24 seconds ago, so that is 384 seconds. This is the activity of the radioactive source. Okay, you have to work backwards in this case. Okay, so that is the end of this lesson. So in this lesson, we have covered what is half-life. So remember, what half-life is a quantity of time, and it is the time it takes for the radioactive nuclei to decay by half. To find half time, what you need to do is you figure out um, when it becomes half. Okay, and when you do calculations with half-life, it's a bit tricky. You have to use, there's no formula, so you have to use your common sense and logic. Have some sort of timeline or table. So you either have to work forwards and half the radioactivity for every time, or you work backwards and double the radioactivity every time. Okay, so we will stop there. I'll continue and talk about the uses of radioactivity in the next lesson. Until then, stay safe. Assalamualaikum warahmatullahi wabarakatuh.